The talk we have now is by Qian, and it is about how much can commodity hardware help on closing microarchitecture timing channels. So let's welcome Qian.
Hello, I'm Qian Ge. So today I would like to share with you some experience we had on trying to closing microarchitecture timing channels with hardware-provided operations. This work is done together by Yoel, Frank, and Gernot. So what this talk will be about? This talk will be about timing channels, and will be about building timing channels on shared hardware. And lastly, it will be about our experience on closing these channels. So after the talk, if you have interest in the contents, please just feel free to download our paper, which is currently published as a preprint. The name is Your Processor Leaks Information, and there's nothing you can do about it. Okay, so as I mentioned, this talk will be about timing channels. What is timing channels? The timing channel is done by exporting timing variations for communication. So apparently, for building these timing channels, we need time. We need a time source to measure something. And how would the information be leaked? It's leaked by either fast or slow progress of a thing. Later on, along this talk, we'll learn about how these timing channels will be built on shared hardware components. So the timing channels and timing attacks normally has two formats. One is covert channel, and secondly is side channel. So the covert channel is a Trojan trying to transmit information to a spy through its own execution, forcing the hardware into a particular state. So here we demonstrate a Trojan trying to leak information to a spy through a covert channel, right? And side channel is similar with covert channel, but the main difference is side channel is a spy trying to recover sensitive information from a non-colluding victim. So here we demonstrate example where a spy trying to steal a private key that is used by a cryptographic algorithm, right? So we say that a side channel is a special case of covert channel. The existence of covert channel represents the potential of side channel. Why we say that? It's because they're using the same technique. Demonstrating a covert channel, i.e. demonstrating the technique, is much simpler than demonstrating using the same technique to build a side channel to stealing some secret. So our research is trying to solve this question. How effective is existing architecture support for closing microarchitecture timing channels? And what we actually discovered is the timing channel based on shared hardware components cannot be closed with all the available hardware flashing operations. And even though the countermeasure that recently provided by Intel for a temporary microcode, which is a temporary microcode fix for the Spectre attack, cannot be used for mitigating the attacks based on the branch prediction unit. It was fairly effective on old cores, but not much on more recent cores. Okay, so the threat model we used for this research or this study is a covert channel, where we're having a Trojan and spy. They try to leak information through a shared piece of hardware. More specifically, we have a Trojan who execute within a restricted domain. And we're having a spy, which also executed on the same piece of hardware, but is outside the restricted domain. And they having a time shared use of a core. We say that this attack, our research is trying to build, the timing channels on the shared hardware components. But how to build timing channels? The foundation of building this timing channel is by creating resource contention on the shared hardware components. And we're targeting on those components that within a core, right? So these components, now we're speaking, are the level 1 caches, that is level 1 instruction cache, level 1 data cache, the branch target buffer, and branch prediction unit, for example. And we say that the contention can be used to transmit information. But how exactly that will be used for transmitting information? In order to understand that, we need to understand how the cache works. So assume now we're having an n-way associative cache. What is cache used for? It's used for shorten the gap between the CPU, shorten the frequency gap between the CPU and the memory, right? So what that means that it is contain the memory contents that has been most recently visited. If I have a program, I try to visit some data. First of all, I need to search the cache. I see my contents in the cache or not. If it is within the cache, that's a cache hit, right? So that will be served directly from the cache. If it is not within the cache, I need to go all the way down to the memory and fetch it in. That is much slower process compared with cache hit. That is cache miss. So because this fast and slow can be measured by time, it can actually be used for building a timing channel. And before we actually go into the actual timing channel techniques, I want to briefly introduce how would cache misses happen. There are 3 types of cache misses. One is compulsory miss, which means that you'll definitely hit a cache miss for the first visit. A second would be capacity miss, which means that the cache size is limited. Whatever you need may not be hosted all in the cache at the same time. And most importantly, that is related with timing channels, that will be the conflict miss, which means that the same cache line is happen to be used by different programs. And in the timing channel scenario or the cover channel scenario, that is the Trojan trying to create conflict miss, and the spy can detect this miss using a time source. Right, so here we actually come down to a concrete example of how to build this timing channel attack. And here we gave you an example of this primer probe attack technique. This attack is actually used by here a spy and Trojan. They're trying to convert information through a shared piece of cache. And this attack including 3 steps. First of all, prime. That means that the spy trying to prime a cache set with its own cache lines. And then it waits a bit, let the Trojan have the chance to either evict or not touch any cache lines. And eventually, the spy will probe again, trying to timing the cache line that is set previously. So that the probe time actually tells the Trojan something, right? It tells if the probe time is longer, that means that the Trojan was previously trying to evict some cache line and it succeeded. That could be means that the Trojan was trying to send in information bit 1. If the spy doesn't detect any changes in its probing time, that means that the Trojan hasn't touched any line before, and that means the Trojan was trying to send him bit 0, for example. And this particular actually attack technique has been demonstrated before on the cloud-based scenario, where we're having a spy that hosted by a Linux virtual machine successfully conduct a cryptographic attack, which breaks the Elgamal private key that is actually used by some other algorithm inside another Linux virtual machine. So this previous work actually demonstrates this attack is practical on the cloud as well. And now we know the techniques and how this timing channels is built. Think about it, we can actually know that the timing attacks are possible everywhere. That means that wherever the resource containment is possible, we can see a time attack. That could be possible mean the attack can be between the applications that authored by different developers that running on the mobile phone, or could be that the attack could be between the workloads that conducted by mutually distracted users that hosted by cloud provider. What is more severe, it could be conducted between the untrusted and trusted components on the military platform where those components share a piece of hardware. So what we learned so far? We learned that the microarchitecture attacks, for building it, we need two factors. We need a timer, that is a time source to measure our progress. And we also need ability to create resource contention. So in summary, the existence of microarchitecture time attack is because the execution of previously running program can affect the performance of current running program. That's a key of making a timing channel work. So just building the channel is not enough, right? So for doing a research study, we also need to visualize and represent the channels that whatever we build and measure. In this work, we're trying to use the channel matrix graph to demonstrate the resource contention between the spy and victim, spy and the Trojan, right? So with the hope of we can translating the resource contention into colors. Here we're having an example of the channel matrix. And the color in this graph indicating the probability of observing a particular output Y for a given input, and as per the scale on the right. What does that mean? That means, for example, we'll be highly likely to observe an output as 24,000 for a given input X 250 than all the other X's. And in this work, all the experiment all those experiments we set in this way. We are set it as a cover timing channel on the shared piece of hardware. So here we're having that cover timing channel built on the shared cache that is using prime and probe technique. What we have again is we're having a Trojan and spy. They're executing on the different security domains. They're having a time-shared user core. They're separate but not allowed to talk. So the Trojan here, whenever it runs, it's trying to change the number of cache sets that it uses on each run. We're regarding that as input X, right? And whenever a spy runs, the spy tries to measure the total cost of probing a buffer, and that is regarded as output Y. So now we know what is X. X is the number of cache sets used. And what is Y? The Y is the total time in the CPU cycles for probing the buffer that is measured by the spy. Okay, so now we learn how we set up this experiment. Let's bring the meaning into this graph. What we can see here, we can see that when the X increases, we highly likely have an increased Y. That means that the heavier the contention created by the Trojan, the longer the probing time detected by the spy. So another way to say that the probing time measured by the spy is highly influenced by the cache contention created by Trojan. That is actually demonstrated in this heat map. So only demonstrating the contention would not be enough, right? So any study or research, you need a number to represent the result. And in this study, we choose to use channel capacity to represent the capacity of the channel we measured. In this particular example, that just a graph we show here, this is the channel capacity is 4.0 bits per usage. That means that after each run of the Trojan and spy, they maximally can leak information 4 bits. And in terms of the channel bandwidth, that is calculated by multiplying the capacity by the input symbol rates. So this experiment setup, the Trojan and spy, they can have 500 runs per second. And therefore, the channel bandwidth would be 2,000 bits per second for this experiment. So hardware cache flashing operations has been long believed as a very reliable method to mitigating cache-based timing channels, because it is believed as a reliable method to resetting hardware to a defined state, right? And this has been, mentioned and referenced in a lot of previous study and literature. The good thing about this, it doesn't cost much, because if you think about you flashing a small cache, right? The L1 data cache on all the most recent x86 platforms, that is only 32K. And the contents that left in the cache after context switch will be code anyhow, and flashing costs won't be much. And the downside of it is you relying on hardware manufacturer support for doing these operations. So this sounds very simple and easy, right? So you just conduct hardware cache flash during a context switch and making sure the cache will always be cold after the kernel exit. But no one so far has been asked the question, does this method actually work? And that actually brings the scope of our work. We are trying to examine the hardware support for eliminating microarchitecture timing channels with the hope of trying to answer this question. Would the channel still be able to observable while all the hardware mitigation operations are all engaged? Therefore, we designed this work as the following. First of all, we implement multiple cover channels. And secondly, we identify the processor instructions that can be used for mitigating these channels. Thirdly, we measure the channel capacity with and without the mitigation technique. So it sounds very much straightforward and simple, right? So in terms of the microarchitecture timing channels, what we actually implement is we implement a form of prime and probe attacks on all the intra-core cache-like components. And these are the L1 instruction cache, the L1 data cache, the table lookup set buffer, the branch target buffer, and branch history buffer. Remember, the tag rebuild or the prime and probe technique, it is all about creating conflict misses, right, as we mentioned before. So how we created conflict misses on these different hardware components, it just depends on how these hardware components work. So the L1 instruction cache, because it actually caches instructions, we're creating the conflict misses by executing chained jump instructions. The L1 data cache, as most people know here, It is caches the memory contents that used for reading or writing a buffer. Right? So we're creating the conflicts by reading a buffer. And the table look-aside buffer, it is work as a cache for paging. Right? So for the pages, the memory pages you visited. Therefore, we're creating conflicts by visiting pages. The branch target buffer is actually caches the destination of the jump instructions. Therefore, we're creating the conflicts by executing jumps. Lastly, the branch history buffer is used for caching the result or the history of conditional branch instructions. Therefore, we're creating the conflicts by taking or not taking the conditional branch instructions. Okay, so now we know that how many paths we're going to run, but where are we going to run it? So we choose to run these cover channels on both x86 and ARM platforms. And we select 3 x86 testing platforms as well as 2 ARM testing platforms. For the x86 platforms, we choose to use Sandy Bridge, Haswell, and Skylake. And that represent 3 different generations of x86 platform. And for the ARM platforms, we choose to use the ARM Cortex-A9, which is an implementation of of ARM v7. And we also use Cortex-A53, which is implementation of ARM v8. So if we look at the manufacturer year of these platforms, we can see that we actually selectively selected these platforms along the generation. We hope our result will be representable for different type of microarchitectures. So in terms of what we use as hardware for flashing the hardware state left by the previous running program, we actually spend a lot of time digging the hardware programmer manual and trying to find what is offered by the hardware manufacturer. So this table here lists what we actually find and what we use eventually. I'm not going to the details what is listed in this table. Rather than going to the details, I would like to give audience 20 seconds to look at this table to see what is inside. While you're looking at it, I would ask a small favor. Could you actually using a short sentence or one sentence to summarize what is inside? I see people shaking their hands. Okay, so I'll try to summarize it because I've been spending so much time on trying to understand my work and presenting my work in front of people. But so this table actually trying to list all the information we gathered that offered by both x86 and ARM platforms to flashing the different part of the hardware, right? We see that we're having the upper level cache, TLB, branch predictor, prefetching, and something else. I felt that was a very long sentence. The message I actually trying to deliver to every of you is after you spend so much time digging the programmer manuals, you find there is actually no systematic way to describe and summarize the current state. Right? You don't really know what is offered by the hardware manufacturer, and you cannot confirm that easily unless you're making sure you read every piece of information in the related section. On x86, this could be easier because x86, you only need to understand one big menu that's 2,000 pages. For example, you know where things are. But on ARM, that is a little bit more difficult because ARM, for example, ARM v7 has its own programming menu. And any implementation of it also has its own programmer menu. Right? So ARM Cortex-A9 has its own programmer menu. But anything externally, like how to flashing the L2 caches, is actually indicated in another separate menu that is used as the L2 cache controller menu. So that means that the methods are very specific on different architectures. And we can see a very huge gap between the ISAs, that is instruction set architecture. ARM and x86, they actually offer different things. You don't know what you expect until you really, research and searching to trying to understand and confirm it. What is more interesting is there is no hardware support on either disable or flashing the instruction prefetcher. In this table, we can see there is some architecture can give you support on disable or flashing the prefetcher used by data, but there is none provided for prefetching instruction because instruction prefetching is highly related with your program performance that need to be protected. Okay, so in this work, the system setup we use is we actually use a separation kernel configuration of the XCL4 microkernel. What does that mean? What does the separation kernel configuration mean? That means that we use a round-robin scheduler, and only timer interrupt is allowed to trigger the switch between the Trojan and spy. And the Trojan and spy, they use physically destroyed memory, physical memory. This system setup is actually as much separation as a system can offer, which means it is the best case for mitigating timing channel or do any timing channel study. And we're doing the cache flashing operations that we previously mentioned, that all of them in a big table during context switch. So before we're actually going to see the result, I would like to spend a little bit time introducing the format of our result. So we're going to list all the channel capacity with and without mitigation in the cell, right? And that's for all the testing machines for all these implemented channels, right? So we have in channel from the top to the bottom, that'll be the L1 data cache, L1 instruction cache, TLB, BTB, and branch history buffer. So in each cell, at the left side, that is unmitigated channel capacity. So if we can see a channel there, that means that we successfully implement the channel. On the right side, that is the right side value is the maximally mitigated channel capacity. So that is a capacity we measured after we conduct or implement or engage all the hardware provided cache flashing operations or hardware resetting operations. So the number in the parentheses, it is the statistical bound allowed by the simulation test for a zero capacity channel. Because this study is done by experimental work, and for doing experiment, there are probably some chance of having the sampling errors. Therefore, we would like to have an idea of is the channel we see is due to the noise, or there is actually a channel, right? So we gave in a statistical test on what the zero capacity channel would be, and that is in the parentheses, the number. We say that if a mitigated channel capacity is larger than the statistical bound, therefore the channel is highly likely to be real. So here comes to our result, what we actually discovered. We actually see that for the channel we implement here, we successfully implement all the channels, right? But what is more important, most interesting is none of the mitigated channels we see at the right-hand side in each the cell is larger, or sorry, it's smaller than the statistical bound, right? So it's highly likely the channel, even after all the mitigation method involved that provided by hardware manufacturer, is still a real channel. And all these red numbers we highlighted here is the case where we can see from the visual representation as a heat map that we introduced before that there is a definite channel. So I'm not going to tell you to give all the details of our discoveries, but here I would like to give a highlight about what we found for using the cache flashing operations to mitigating the L1 instruction cache channel. So that is, remember the big cell here? We enable all this method across all the testing platforms during the context switch. But we still be able to actually observe L1 instruction cache channel on all the testing platforms. So we have seen some example of what a channel looks like in the heat map. But here is an example of what would be a close to zero capacity channel look like before we're actually looking at the bad guys. So what we actually want to look if that's a zero capacity channel, it is we see Y is evenly distributed for all the axes, right? We see a very, no matter how wide the bar is, we see an even spread. That means that we cannot guess just based on looking at Y, what X could be for that run. Okay, so previously we mentioned that people normally believe flashing caches can actually mitigate all the cache-based timing channel. And this is a result. On the Sandy Bridge, we use the cache flashing operation provided by x86 for mitigating the L1 instruction cache-based channel. And we see the operation is only moderately effective. It only can reducing the capacity by 64%. Another way to say we cannot fully mitigate the channel. Why we say that? You see this, the visual representation we're having here. When the X is between, let's say, 1 to 5, we definitely can observe a high, the Y is definitely having a higher average than all the other Y that is affected by or influenced by the other axis. As a result, we can conclude that the cache flashing operation doesn't work. It cannot mitigate the L1 iCache based channel with the cache flashing operation. What about, well, we see the cache flashing operation doesn't work, right? So what about if we engage everything that is provided by x86? That including the TLB flash, disable data prefetching, and cache flashing operations. That is the big hammer, as much as you can ask from the hardware manufacturer these days, x86, right, Intel. And we still be able to observe the channel with those engaged. And here still, right, so when X is between 1 to 5, we definitely will observe Y. The average of Y definitely higher than the rest of the Y. That is influenced by the other axis. So we say that the channel is still observable. You can see it from the graph. Okay, that is interesting. I think it's interesting. What else we found? We found a similar story with branch target buffer unit and branch history channels. It's because there's no specific mitigation available for targeting, resetting the state left on those components. What is more is the TLB channel cannot be mitigated with TLB entry flashing operations. I would like to refer the paper for details. So people may ask, what about the Spectra mitigations provided by Intel? Right? Spectra was such a big thing, during the Christmas and even New Year. It's like jumping an information bomb in front of people saying Happy New Year, right? So what about the mitigation method introduced by Intel for mitigating Spectra? Intel introduced a set of mechanisms that is called indirect branch control, and that is enabled with some kind of microcode fix, which you can use for mitigating that particular attack. But it doesn't declare itself to clear branch predictor state. Even though that's the case, we still apply the temporal microcode fix for the Spectrum attack on our testing machine to see how it goes. Why we call it temporary fix is because shortly after that, after it released, Intel recalled its microcode fix because people find a severe rebooting problem on certain microarchitectures. Therefore, it was recalled. Anyhow, so after we applied that temporal microcode fix, what we discovered is the branch target buffer channel capacity reduced more than 50% on Haswell machine, but not so much on Skylake. And what is more interestingly is the branch history buffer channel reduced to almost zero on Haswell, but it doesn't change on Skylake. What we learned from that is the indirect branch control mechanism that offered by Intel can close the channel, but is only on certain testing platform, or is effective to close the channel, but only on certain testing platforms. So just to summarize what we found is the cache flashing operations cannot fully mitigate the intra-core timing channels. That is contrary to the common belief, what people believe, cache flashing operation can actually flush them. And as a result, we demonstrate that many microarchitecture features aiming at improving average case performance, they're producing high capacity timing channels that cannot be closed with any available hardware provided countermeasures, even including those often suggested for closing the particular channels, and despite some of them being very expensive, right? So what we show is the big hammer offered by hardware manufacturer doesn't work as people expected. So some people ask me the question, what about SGX? Could SGX do better? So SGX, by definition, it provides logical data flow out of enclave by encrypting the memory and scrubbing register values when there is an enclave exit. It doesn't scrub in state unless it's directly observable. Another way to say, timing channels are outside their thread model. So SGX doesn't prevent timing channels. As a result, recently there are lots of research and literature published the actual real attacks that demonstrate timing channel attacks inside the SGX. So another question people may ask, okay, now we see the hardware flashing operation doesn't work. What about software scrubbing? Can I build some software, piece of software to try to, with the hope of erasing the hardware state? So the problem of using the software scrubbing is it requires a correct understanding of the hardware state. And that is very hard without support of official documentation. And for people actually, working, trying to understand how this caching works inside a CPU, whatever CPU you're using, you will know that this is basically nowadays impossible, and it's not conveyed by the manufacturer. If you want to reverse engineer the details of how this hardware components works. It is very hard as the current hardware platforms are too complicated to understand because we have so many components that including the prefetchers and the branch history buffer and the replacement policy used by the cache components. Every tiny details of how these hardware components work is actually highly related on how reliable the software scrubbing method is. And think about these details will be changed in each chip step, right? Therefore, I personally believe guesses about their operations cannot be validated, cannot be used for support an effective defense. So we all see what the current look like. What about the future? What can be done better? What can we offer? We argue that there must be architecture mechanisms that are provided by hardware manufacturer for flashing all the hardware dependent on core state. And what is more important for providing them is you shouldn't affect the performance where they're not needed. For example, on current x86, there's no way to selectively flashing a level of the cache. Right? So Intel only offer an instruction for flashing cache lines that contains in all the level of caches. What we see from the spectral attack, the spectral defense that are provided by Intel is the channels can be closed if the hardware manufacturer wants. But we see that the branch history buffer channel was actually closed almost down to zero on the Haswell platform. That was a rapid fix that conducted by Intel for mitigating the spectrum. What else can we do? I think we can offer some dedicated hardware design that just use as a sandbox for running very secure software or a piece of software that need to be highly trusted. Or there could be any other kind of hardware design which give you, isolation from the rest of the system. Okay, so that brings to the end of my talk. What I was trying to tell everyone here is the timing channel exists, you cannot stop them, and we need new hardware. If you're interested in this topic and related work, please feel free to take a look at our previously published work, and we also have a website that contains the current status of this research in this topic, that's timing channel topic, conducted by the Trustworthy System in Data 6.1. Thank you very much.